Okay, welcome to lecture 24. So we're still in unit 3, the Laplace transform. Today we're going to be covering, revising really, partial fraction decomposition. But I wanted to just flick back to the previous lecture first, just to motivate that a little bit. So in this question here, we were asked to, this is at the end of the last lecture, we were asked to find the inverse Laplace transform of this function here, which basically was a polynomial divided by another polynomial. Okay, and it turned out that we could complete the square on the denominator of this polynomial, and when I completed the square, I got this s plus 1 term both on the numerator now and the denominator. Okay, so that meant that I could identify this as some kind of exponential times a cosine. Okay, it turns out that try to find the inverse Laplace transform of the dividing two polynomials. So one polynomial divided by a second polynomial. It turns out this is a really common problem that occurs when we're trying to solve initial value problems using the Laplace transform method. But it doesn't always work out when we complete the square that we get this nice form that we can recognize as some kind of cosine or some kind of exponential times a cosine. So in fact what we need to do quite often is use partial fraction decomposition to simplify these ratios of these polynomials. So let's say we have two polynomials, p of s and q of s, and the degree of the polynomial q, so the polynomial on the bottom, is a higher order polynomial than the one on the top, p. If it was the other way around, you could just simplify this using long division, right? So if you had like a quadratic on the top here, and let's just say a linear polynomial on the bottom, then you would just simplify that using long division. Okay, but let's say we've got the degree of q of s, that polynomial is greater than the degree of p of s. Then we're going to simplify this using partial fraction decomposition. Okay, and so again, like I said, this is going to pop up a lot when we're solving initial value problems. So there's three cases for the polynomial q that we're going to consider. When q has non-repeated linear factors, when q has repeated linear factors, and then when q has quadratic factors. So focusing firstly on non-repeated linear factors, so that means that we can write q like this. So s here is the variable, so s minus some number r1 multiplied by s minus some number r2. If we got an nth degree polynomial, then we have n of these terms, so s minus some number rn. So the r sub i's are all real numbers, real constants. Okay, so if it turns out that q can be written as the product of non-repeated linear factors, then our ratio p over q can be written as a over s minus 1, this first term up here, plus a2, so a1, a2 through to an are just real numbers, so constants. So plus a2 over s minus r2, the second term there, all the way through to an over s minus rn. Okay. And so obviously we're going to probably deal with not too many terms here, but let's look at an example. So we want to find the inverse Laplace transform of s divided by s minus 1 times s plus 1 times s minus 3. So obviously the degree of the polynomial on the numerator here is 1, and the degree of the polynomial on the denominator is 3. So this is really saying, well, let's use partial fraction decomposition. You can see on the bottom here we've got non-repeating linear factors. There's only one s minus 1, there's only one s plus 1, and only one s minus 3. So what I can do, according to this partial fraction decomposition, is I can write this s over s minus 1, s plus 1, s minus 3. I can write that as some number a1 over s minus 1 plus some number a2 over s plus 1, the second term there, plus some number a3 over s minus 3. Okay, so here I'm identifying my P of S as being S, my Q of S as being this denominator, the product of these three linear factors here. Alright, so now this term on the bottom here, this equation on the bottom here, so P over Q equals this thing here. We need to find the values of A1, A2, and A3. Remembering that A1, A2, and A3 are just constants. So what I'm going to do here is this term on the bottom here that I've circled in purple, I want to multiply both sides by that term. Okay, so multiply both sides of this equation by S minus 1, S plus 1, S minus 3. So if I do that, the left-hand side, we're just going to get left with S, okay? Yeah, clearly. A1 over S minus 1, well, we're going to get an S minus 1 cancelling here. So we're just going to get A1 times S plus 1 times S minus 3. And similarly, in each of these other terms, we're going to get one of these linear factors cancelling and then multiplying the A's by the other two linear factors. So we get S on the left side, A1 times these two linear factors, A2 times these two linear factors, A3 times these two linear factors. So we need to find values for A1, A2, and A3. Okay. Just give myself a little bit of space here. Well, I'm going to say, well, what happens when S is equal to negative 1? Okay, well, this left-hand side, when S is equal to negative 1, that's just equal to negative 1, right? But what happens on this right-hand side? Well, I get A1 times negative 1 plus 1, which is 0. So I get 0 here. I get A3 times negative 1 minus 1 is negative 2, times negative 1 plus 1 is 0. So this term becomes 0 as well, and I just get left with the A2 term. So I get negative 1 is effectively equal to A2 times 8. So I get A2 is equal to negative 1 over 8. Okay, great. So that was for S equals negative 1. Let's try S equals 1 now. Because if I do that, the A2 term cancels because we get 1 minus 1 is 0. The A3 term cancels because we get 1 minus 1 is 0. And we get left with this A1 here. We get S is 1, so 1 equals A1 times 2 times 1 minus 3, which is negative 2. So if we solve that, we get A1 is equal to 1/4. Okay, we already had A2 as negative 1/8. And finally, let's let S equal 3. And if we do that, again, this A1 term is going to be 0 because we get 3 minus 3 is 0. The A2 term is going to be 0 because we get 3 minus 3 is 0. And we can find that A3 is equal to just simply 3 over 8. Therefore, we were taking the inverse Laplace transform of the original function, S over this thing here. We can write that as A1 over S minus 1, so negative 1/4 over S minus 1, plus A2, which is negative 1/8, so negative 1/8 over S plus 1, plus A3, 3/8 over S minus 3. Well, the Laplace transform is linear, so I can evaluate each of these individually. In fact, I can pull out these constants, negative 1/4, negative 1/8, and plus 3/8. I can pull those out front as well because it's just a constant, and the Laplace transform is linear. So, well, we're effectively taking the Laplace transform of 1 over S minus 1. Well, that's just an exponential of t, right? Inverse Laplace transform of 1 over S plus 1, well, that's going to be the exponential of negative t and positive 3t here. So we end up with the inverse Laplace transform of this fraction is equal to this thing here. And we really only could do that because of the partial fraction decomposition, simplifying into three things that we knew how to take the inverse Laplace transform of. Okay. So again, you really need to know your Laplace transform table, or at least have it in front of you so that you can refer to it and say, well, what function if I take the Laplace transform of it, gives me 1 over S minus 1. Well, if I take the Laplace transform of e to the t, I get 1 over S minus 1. Okay. Case 2, we have repeated linear factors. So Q contains the repeated factor S minus some number R to the power of m, where m is some integer. Okay, so if we have this situation, then P over S becomes A1 over S minus R plus A2 over S minus R squared all the way through to AM over S minus R to the power of M. All the A's are real numbers. So for example, if we have S squared over S minus 2 squared times S minus 3, we have a linear factor here. S minus 3 is a linear factor. But here we have a repeated linear factor. So S minus 2 is repeated 2 times, right? It's squared here. So we know that we can write P over Q, which is S squared over S minus 2 squared S minus 3. We can write that as, okay, well this last term here, B1 over S minus 3, that's just our linear factor that comes from S minus 3, so it's nothing special. But the S minus 2 squared bit we can write as A1 over S minus 2 plus A2 over S minus 2 squared. Okay, and we're going to play the same game as the last example. We're going to multiply both sides of this equation by the denominator of the left-hand side. We're going to multiply both sides by S minus 2 squared, S minus 3. So that on the left-hand side we just get S squared, and on the right-hand side we get something that looks like this. Okay, just simplifying that, give myself a little bit of space. I'm going to approach this in the same way. I'm going to let S equal to 2 here, because then A1 is going to be A1 times 2 minus 2 is 0, so that's term's going to disappear. The B1 term, 2 minus 2 is 0, so that one disappears. We just get left with A2. Okay, so we get left with 2 squared is 4, plus A2 times 2 minus 3 is 1 is negative 1. 2 minus 3 is negative 1. So we find that A2 is equal to negative 4. Okay, what about S equals 3? Well, the left-hand side becomes 9. A1 times 3 minus 3 is 0, so that one disappears. A2 times 3 minus 3 is 0, so that disappears. And we get left with 3 minus 2 is 1 squared. 1 squared is 1. So we get left with 9 is equal to B1. So B1 equals 9. Okay, but now we're in trouble because we've used S equals 2, S equals 3. And that was nice because it cancelled out. Two of our terms, and we just got left with, in the first case, A2, and in the second case, B1. But there's no other numbers we can multiply by now, or we can set S equal to now to solve that equation. So what I'm going to do is I'm just going to look at the S squared terms. Okay. So for example, on the left-hand side here, I have one S squared term here. On the right-hand side, I've got A1 times S squared here. So I've got an A1 times S squared term here. There's no S squared terms in A2, it's just linear. And there's an S squared terms times B1 here. So I can write A1 times S squared plus B1 times S squared equals S squared. Or A1 plus B1 equals 1. I already know what B1 is, so I know that, in fact, B1 is 9, so I know that A1 must be negative 8. So therefore I can write this, the inverse Laplace transform of this fraction of polynomials, like so. So instead of writing this complicated thing as a fraction of polynomials, I'm just looking at the inverse Laplace transform of some constant times 1 over s minus 2, some constant times 1 over s minus 2 squared, plus some constant times s minus 3. Some constant divided by s minus 3. And again, well, you can identify these constants as being a1, a2, and a3. Again, some of these are quite easy to take the inverse Laplace transform of, because if I took the Laplace transform of e to the 2t, the exponential of 2t, then I would get 1 over s minus 2. So this inverse Laplace transform is going to be an exponential of 2t. Similarly, at the end here, 1 over s minus 3, well, I know that's the inverse Laplace transform of that is going to be the exponential of 3t, because I know if I take the Laplace transform of the exponential of 3t, I get 1 over s minus 3. This one in the middle here is a little bit trickier. Well, I've effectively got 1 over s squared, right? If I forget the negative 2 for a minute, I've got 1 over s squared. I know that if I take the Laplace transform of t, I get 1 over s squared. So I know that this is going to be the inverse Laplace transform of 1 over s squared is t. If I use the first translation theorem with a equal to 2, then I can recover this negative 2 term as well, right? So it turns out that this inverse Laplace transform is given like so. So I'd really encourage you to go back, well, maybe even pause the video now, and just as an exercise, just calculate the inverse Laplace transform of each of these terms individually, and just make sure that you get the same thing that I do, just as a bit of practice for finding the inverse Laplace transform. Okay, so we've looked at two cases now. We've looked at linear factors, which were discrete linear factors. They were not repeated. We've looked at repeated linear factors, and now we're going to look at quadratic factors. So if Q of S, that's the denominator of this ratio up here, contains a quadratic factor, so alpha and beta here are just real numbers. It can be any real number. M is a real number, but it's also an integer. So if we have something that looks like S minus some constant squared plus some constant squared all to the power of m for an integer m, then we can rewrite the ratio P over Q like so. C1 times S plus D1 over S minus alpha squared plus beta squared plus C2 times S plus D2 S minus alpha squared plus beta squared all the way through to the mth term. So in this case, we're trying to solve for these constants C1 and D1, C2 and D2, Cm times Dm. Obviously, this begins to look really messy really quickly, so often you'll see m is equal to 1, maybe 2 maximum in this class, because otherwise it's just too much work. So as an example, let's look at, we've got a quadratic on the top here, and we've got something that's, well, s squared times s, so we've got a cubic on the bottom, so the degree of the denominator is larger than the degree of the numerator. We've got a linear term here, a non-repeated linear factor here, and then here we've got a quadratic term, okay? So, in fact, I can simplify that quadratic term like so, right? I can complete the square on this quadratic term, so I get, well, I've still got the numerator the same, the s minus 2 is the same, but if I complete the square on this quadratic in this bracket here, I get s plus 1 squared plus 4 plus 2 squared. Okay, so this is a quadratic term here. So according to my partial fraction decomposition, this fraction here can be written as the linear term here, a1 over s minus 2, plus c1 times s plus d1 over s plus 1 squared plus 4, or 2 squared. Okay, so I'm going to do the same thing. I'm going to multiply both sides by the denominator of this left-hand side. Okay, so if I do that, then the left-hand side is just this quadratic on the top, 7s squared plus 23s plus 30. And the right-hand side is something that looks a little bit complicated, but we can solve for it. So firstly, let's let s equal to 2. Okay, so if I do that, well, the left-hand side becomes 7 times 4 plus 23 times 2 plus 30. The right-hand side, well, this term sticks around. We get a1 times 2 plus 1 is 3, squared is 9, plus 2 squared is 4, so 9 plus 4, 13. So 13a1. S minus 2, 2 minus 2 is 0, so this term disappears, and also the d term as well disappears. So we end up finding that a1 is equal to 8. Okay, good. Now I'm going to let s equal 0, and that's because, well, if I do that, we get 0, 0, we get 30 on the left-hand side. The a1 sticks around here. We get 0 plus 1 is 1, plus 4 is 5, so we get 5 times a1. This term disappears, though, because s equals 0 here, so this term disappears, and here we get negative 2 times d1. But we know that a1 equals 8, so we can substitute that into this term here, and if you solve for that, you might like to check, but you get d1 equals 5. And then finally I can let s equal to negative 1. The a1 term here is going to, this one's going to be 0, but in fact we're going to get plus 4, so this term is not going to disappear, but we know that a1 is equal to 8, so it's not a big deal. S minus 1 minus 2 is minus 3, but we know that d1 is 5, so it's not a big deal. We can evaluate both sides of the equation to find c1 is equal to negative 1. So therefore, The inverse Laplace transform of this quite challenging looking ratio of quadratic, fraction of quadratics, we can simplify that to inverse Laplace transform of 8 over 1 over s minus 2. Again, that's a linear factor. We know that this is going to be an exponential of 2t, so 8 times the exponential of 2t. And then this quadratic term here. Okay, this one we have to work a little bit harder to find the inverse Laplace transform of. Okay, so let's try and find the inverse Laplace transform of this thing. And the way I'm going to do that is I'm just going to firstly simplify this a little bit. Okay, what am I going to do? Well, I'm going to write 5, the number 5, I'm going to write that as negative 1 plus 6. So I've done nothing here apart from rewrite 5. Well, the numerator is still the same at 5 minus s. This is 6 minus 1 minus s. It's still 5 minus s. I've just rewritten it in a funny way. Okay, well, why do I want to do that? Well, then I get an s, or let's say negative s minus 1, or let's say negative s plus 1. So I get negative s plus 1 over s plus 1 squared plus 2 squared. This term I can already see is going to be some kind of cosine multiplied by an exponential. Okay. And then I get left over is this 6 here, right? So I get 3 times 2 over s plus 1 squared plus 2 squared, and I can already see this is in the form of a sine. If I take the Laplace transform of sine of 2t, I'm going to get something that looks similar to this, apart from the plus 1, but I can use the first translation theorem to solve that too. So let's just rewrite that like so. So we're looking at the inverse Laplace transform of this term here, which we know is an exponential, this term here, which is going to look like an exponential times a cosine, and this term here, which is going to look like an exponential times a sine. So maybe you might like to pause this video and just try and solve that yourself, and then I'll put up the solution to this inverse Laplace transform in 3, 2, 1. Okay, I hope you got the same answer I did. If you didn't, try again. Let me know if you have any trouble. Send me your working if you want to, but I'm just trying to encourage you, please practice. Firstly, practice finding the Laplace transform of functions, but also practice finding the inverse Laplace transform of functions, remembering that whenever we see an s plus 1 or an s minus 1, or you're probably going to have to use the first translation theorem there. So please keep that in mind. Practice, practice, practice. This is something that's brand new to you, right? Laplace transforms, inverse Laplace transform are brand new to you, so it's going to take a lot of practice. And then the rest of the class really today was just reminding you about partial fraction decomposition, because really, if you're going to be solving initial value problems using the Laplace transform, you are going to have to, almost every time, you're going to have to use partial fraction decomposition to simplify your solution and then take the inverse transform. And so that's what we're going to go on to the next class actually, is actually solving some initial value problems using the Laplace transform method. And it's a really powerful method, so yeah, I'm looking forward to it.